All right, so we're talking about special products. We're going to look at two different special products. Okay, here's the first one. We've done a lot of interesting things in the last week or so. We started with common factoring and factor by grouping. Common factoring's big. It's a little wonky on that first day. And factor by grouping is a little weird too. But then we moved on to some good stuff, trinomials and complex trinomials for a couple of days. And now you're probably really starting to get a hang of this factoring thing. And you're probably really starting to internalize these patterns, right? So when we just finished that quiz on expanding and simplifying, you're probably seeing the patterns more now than you did before. How when you multiply two binomials together, you get a trinomial. And so then when you factor a trinomial, you get back the two binomials, right? That pattern of expanding and factoring. And that's the whole idea of how do we get there in the first place. And you remember when we first looked at these expanding questions, this is what I talked about, is look for the patterns. Look for what happens when you expand what you end with, and we use those patterns to go backwards. So we did spend a day on expanding special products. So now we're going to look at factoring special products going the opposite direction. So what do we notice? What are the patterns that we notice here? X minus 3 and x plus 3. The same thing in both brackets, but one's plus and one's minus, or one's minus and one's plus. And what's the result? This is the kind where there's no middle term, right? You'll almost always get 3 terms when you expand two binomials, when you multiply two binomials. And then there's this one special case where you only get 2 terms. And that's it. And so we notice that the first term here is the first term of the binomial squared. It's x times itself. And the second term is the second term in each of the binomials times itself. 3 times 3, or 3 squared, 9, right? So it's got 2 terms and it's got a minus sign between them. And that's what this says. Each term in the expanded form is a perfect square. There's 2 of them, and there's a subtraction sign between them. That's why we call this a difference of squares. So when we're identifying the type, we spent some time yesterday thinking about the difference between a simple trinomial and a complex trinomial, and we identify them by their name. Oh, that's a complex trinomial because it has a coefficient, right? It's got a 2x squared, not just x squared. Oh, that's simple because it's just x squared, right? So we identify them by their name, the type of the factoring question by its name. So this one has a special name, difference of squares. And the name describes it. It's a difference of 2 squares, one minus the other. And look at all of them. X squared is a perfect square, and 16 is a perfect square. What about this one? It's got a 9, that's a perfect square. It's got an x squared, that's a perfect square. And it's got a 25, that's a perfect square. So all the coefficients, all the variable parts, everything is a perfect square. And every one of them has 2 terms and there's a minus sign between them. That's what you look for when you do a difference of squares. And there's no real other way of doing these other than noticing that that's what's happening and knowing that it comes from this special case where you have like x and 3 and x and 3 and one's minus and one's plus. Or x and 4 and x and 4 and one's minus and one's plus. We just know that connection. We know that pattern. Okay. We talked about the perfect squares earlier in this course. So we talked about them when we were simplifying radicals, right? So what's the list of perfect squares? 1, 4, 9, 16, 25, 36, and so on. And so you need to know those again because you have to be able to recognize when you see a perfect square. Does that make sense? Happy with this so far? That last one is interesting because it's got a 9x squared, so it's still squared. But again, the square root of 9x squared is 3x. Because 3x times itself, 3 times 3 is 9, and x times x squared, x times x is x squared. So how do we use that to factor? There's lots of little things that go into this. One thing I notice is it's not a trinomial like we were doing yesterday and the day before and the day before. Not a trinomial. It's only got two terms. It could be common factor. You always look for a common factor first. That's always true. We don't have to worry about that here, though. It's not a factor by grouping. Those have 4 terms. Trinomials have 3 terms. This one only has 2. The number of terms, we'll talk about this in a couple of days, but the number of terms is a big indicator of what kind of thing you're looking at and how you're going to factor it. So 2 terms. Are they both perfect squares? X squared is a perfect square. What about 100? Is that a perfect square? Yeah, it is. So what's the square root of 100? Somebody tell me that. 10. So how do we write this? 1's plus, 1's minus. How do I know? Because I just know that pattern. X plus 10, X minus 10. Done. I know this because I've expanded these before, and I know that when I expand this, okay, don't write this down, but it would be like negative 10x and positive 10x. They're opposites, so they add to 0, and that's why I get the middle term disappearing, and I only get a result that has 2 terms. Does that make sense? Everybody happy with that? All right. Try the next one. That's how easy it is. This is the easiest factoring question in the world. But you have to just notice those things.
Will they always be perfect squares for us?
It has to be. That's in the description above, right? They have to be perfect squares for it to be a difference of squares. How many people have answered this one already? Who wants to give me the answer? Riley. I thought it was x minus 6 and x plus 6. Wouldn't make a difference. Very good, right? Doesn't matter which order. Everybody always asks that. Doesn't matter which order you put them in. Same thing. Multiplication, order doesn't matter. How did we get that? 2 terms, minus sign between them, everything's a perfect square. What's the square root of 36? 6. What's the square root of x squared? X. Right? That means it's a perfect square, because when you take it, you don't get some weird decimal or something wonky. You get, in this case, a variable, but you still get something that makes sense, just an answer. Okay, good. Try the next one. Everybody's thinking it can't be this easy. It's bound to get harder. He's going to make it harder on us. Not really. This is about as easy as it gets. 2 terms, minus sign between them. Is 81 a perfect square? What's the square root of 81, Kristen? 9. X minus 9, x plus 9. Done. D. A squared minus 4b squared. So it's a little bit different. It's got a b squared in there. But that's still a perfect square. Still only 2 terms because it's 4 times b squared. It's not like 4 plus b squared. That would change things. Okay, so this is still a difference of squares. Every coefficient, everything in there is a perfect square. Notice that you're not looking at the exponent. Like 2 isn't a perfect square, but x squared is a perfect square. We'll talk about that a little bit more in a moment. But so you're not looking at the exponent exactly. You're looking at the whole variable part. So how would this work? Well, it's going to be a plus 2b and a minus 2b, right? Because that way, 2b times 2b is 4b squared, and the middle term is going to add to 0. Is that okay? Okay, so you try that one. So you're asking yourself, is everything in there a perfect square? If the answer is yes, take the square root of 1, take the square root of the other. 1's plus, 1's minus. It's amazing, isn't it? How just a few days ago, We started looking at this and it was all brand new, and now you see all these patterns and make all these connections. You get this. That's really good. That's a good indication that you're making the right connection, that kind of thing. Who can give me the answer to this one? Kareem? Nice. How many people got that? Fantastic. It's too easy, right? Okay, what about this one? Here's a tip. Don't make up your own different way of doing these things. Think about how we've done every one of these questions. Is everything in there a perfect square? Liam says no. That means this is not a difference of squares. So you don't start making up how you factor it. Like people think, well, I can't take the square root of 3, so I'll make one of them 3x and the other one x. No, that's not how this pattern works. This is not a difference of squares. So it does not follow the same pattern. But what do you notice about it? There's a common factor. Very good. How many people noticed that 3 was common between the two things? So always, always, always common factor first. And what do I get when I divide that out? X squared minus 9. And what is x squared minus 9? Tara? What is x squared minus 9? What do you think? A? Jaden? Yeah. What do you call it, Alan?
So 3 brackets x plus 3 and then bracket x minus 3.
Yeah, very good. Megan? Oh, yeah. What is it called? Not quite. No, difference of squares, right? It's called a difference of squares. X squared minus 9 is a difference of squares. That means it's factorable. So let's do it. So Alan already said it. So 3 bracket x plus 3, because the common factor doesn't magically disappear. You still need it. Still part of this expression. If I expanded that last line, I'd multiply the brackets first, then I'd multiply through by the 3, and I'd get back that original question from F. Okay, so look for those differences of squares. If it's not perfect squares, don't make up your own way of doing things. Don't guess. It's probably this. No, it's not. It's not a difference of squares. It's not a difference of squares. You can't do this to anything except a difference of squares. One more. Well, there's a couple more after this, actually, I should say that. What's going on here? What do you notice? What jumps out at you? What kinds of observations do you make, Liam? It's cubed, which is different. Very good. What else? Anang? There's a variable in both. That's different from before. Very good. What else do you notice? Not just what's different, what's the same? How many terms are there? Yeah, there's 2 terms. There's a minus sign between them. 4 and 49 are both perfect squares. Like, a lot of stuff in here screams at me there's a lot of perfect square stuff going on. But is a cubed a perfect square? Can something times itself give me a cubed? No, right, good answer. It can't. So I don't think you need to write this down, but just watch for a minute. A times a is a squared. So a squared is a perfect square. A squared times a squared is a to the 4th. So a to the 4th is a perfect square. A cubed times a cubed is a to the 6th. So a to the 6th is a perfect square. What's the pattern happening here?
Is times plus and dividing is basically minus?
When you're dealing with the exponents, yes. When you multiply, you add the exponents, exactly. Megan? Squares, when you're talking about exponents and variables, a perfect square happens when you have an even exponent. Odd exponents are not ever perfect squares. So a to the 3, a to the 5, a to the 7, a will not work. A squared, a to the 4th, a to the 6th, a to the 8th, a to the 10th will all work. What's the square root of a to the 10th? Liam, what do you think? What's the pattern? Okay. 5, very good. A to the 5th. Got it. Okay. Okay, so a cubed is not a perfect square, and a is not a perfect square. So what do? Yeah, nice. Common factor of a. What am I left with? 4a squared minus 49. See how common factoring is important? And what is left in the brackets there? A difference of squares. 4a squared and 49. It's two of them. It's the difference between them. So I factor that. Any questions so far? No? Okay, we're just going to do a couple more quick examples because I want to make sure everybody's got this, so you can do this one on your own. Okay, do that one. Okay, stop writing. Put your pencil down. How many people did this? No! Is this a difference of squares? No. So you just made that up. That's not what this is. Watch. What is factoring? It's the opposite of expanding. So if I expand this, I better get back to the original question. What's x times x? X squared. X times 4, 4x. 4 times x, 4x, 4 times 4, 16. What's 4x plus 4x? 8x. Is this the same as that? No. You just made that up. Or maybe you did x plus 4x minus 4 because you didn't notice that there was a plus sign between them. We just learned about difference of squares. This is a sum of squares. What do we know about a sum of squares? Nothing, because we haven't learned anything about it. Why do you think we don't know anything about a sum of squares? Because there's nothing about a sum of squares to know, except that it's not factorable. This is not factorable. So if you factored it, you made that up. Be very careful. This is a common mistake that happens all the time. And I can guarantee you, the textbook and myself at some point will give you a question like this to try to trick you. Possibly even on a quiz or a test. You know how as you're working through the homework, every once in a while there's one that's not factorable? But if it's like a trinomial, it's hard to tell. And a lot of people, like especially with complex, a lot of people yesterday and the day before were like, I don't know, I feel like I've tried every one, but sometimes I just can't get it. So how do I know when it's not factorable or when I just haven't got it yet? So on a test, I would only give you a question that you can know for sure is not factorable. Like that. If you see a sum of squares and you're on top of things, you're going to go, that's not factorable. It's tricking me. It's trying to look like a difference of squares, but it's not factorable. Megan. It's possible. We'll see. See how things go. Okay? The only other thing I could ever imagine, and honestly, I don't even usually do this, but what if I gave you something like this? X squared plus 3x plus 100. Everything's positive, simple trinomial. Who can come up with two numbers that multiply to 100 and add to 3 that are like positive numbers? Like that's not gonna happen. That is not factorable. Do you agree? Not factorable. Those are the only kinds of questions I would give you on a test that are not factorable. There's going to be like, let's say 15 factoring questions. There's always somebody who says like 8 of them are not factorable and they're all factorable. Like trust me, okay? I'm not out to get you that way, but I will possibly put a sum of squares to check that you're paying attention. Okay, H, one more question. Whoops. So this one's definitely a difference. Factor that one. Stop. How many people put like 3 and 33 or 33 and 33 or something like that? People do this all the time because 9 is a perfect square. So then we think 99 is like 33, but it's not, right? There is no square root of 99. So again, this is not factorable. That's another one where you could see that on a test. Because you should know that, like, you can't make it up. Oh, it's 33 and 3 because 33 times 3 is 99. That's not how it works. X plus 33, x minus 3. That's not how this works. Only when they're perfect squares, there's two of them, there's a minus sign between them. Does that make sense? Everybody got that? Okay. Next one. That is difference of squares done. Moving on to the next one. Get that done quickly. So what's different about this one? The last one was like x plus 3, x minus 3. This one's x plus 3 and x plus 3. So I know you're still writing, but this is like x plus 3 all squared, right? Or x minus 4 all squared. And what does that give us? This is a much harder pattern. You see that last one was easy. It was super easy. That's the difference of squares is everybody's favorite factor. It's so easy and it's so fast, right? Even the ones that had common factors were still really straightforward and easy. This one's not as hard to see, or not as easy to see. It's a little bit trickier. The nice thing is you don't have to see it when you're factoring, but we're going to do something a little bit later where you do have to see it. So, you want to start looking for these patterns. And once it clicks, it's going to save you a lot of headache and a lot of work and it'll really help. The connection that happens here will really help down the road. So what's happening here? I've got an x, and the first term is x squared. I've got a 3, and the last term is 3 squared, 9. And if you remember when we talked about this, what's the middle term? It's 3 times x times 2. X squared is x all squared, right? X times x is x squared. 4 times 4 is 16. 4 times x times 2, 8. And it has the same sign there as that one. 3x squared times 3x squared, 9x to the 4th. 7 times 7, 49. 7 times 3 is 21 times 2, 42x squared. So you see how they all share that same pattern. We talked about this before. So if I'm going backwards, here's what you want to have written down. Notice the first and third terms are perfect squares. So we're noticing the same kinds of things as we did in the last one. The first and third terms are perfect squares. You got to know your perfect squares. And remember, we talked about this. X to the 4th is a perfect square, so that checks out. The middle term is 2 times the square root of each. So the square root of 9 is 3. Square root of 49 is 7. 3 times 7 times 2 is the 42. It's a little bit harder to see this working backwards. It's called a perfect square trinomial. And it is very important. The connection here is very important down the road. Okay, let's try a couple. This one's kind of tricky. 4 is a tricky number, but is the first term a perfect square? Yep. Is the last term a perfect square? Yep. So this would be like the square root of x squared is x. The square root of 4 is 2. 2 times x times 2 is 4x. So yes, this is a perfect square trinomial, which means I write it like this. See, the thing about this is you can do it the other way. It's a simple trinomial as well. It's not like it's different. Two numbers that add to 4 and multiply to 4, 2 and 2. And you can do it that way, it's fine. But perfect square trinomials are something that we need to start paying attention to. Okay, let's try the next one. There's only a couple of these to try. First term of perfect square, yes. Last term of perfect square, yes. What's the square root of 36?
6.
So 6 times 1 times 2 is a 12. So yes, this is a perfect square. Shares the same sign as that middle term. If you're not seeing it and you think this is like voodoo magic, remember it all comes down to how did we get there in the first place? You have to see that connection. Okay, try C. No common factor here. There's no trick like that. So it would be a complex trinomial. Two numbers that you'd have to do the dance for this one, right? Looking for the factors of 4, look for the factors of 25. Not a ton of them, but it'd be a little bit of work. But what kinds of questions, like how would you even think that this might be a perfect square trinomial? Well, 4x squared is all perfect squares. 25 is a perfect square. Once I see all those perfect squares, I would ask myself, wait a minute, what's the square root of 4? It's 2. What's the square root of 25? 5. What's 2 times 5 times 2? 20. Perfect square. So 2x plus 5 all squared. It's not as obvious. It doesn't jump off the page at you like the difference of squares do. Okay, but once you just think about it a little bit, you get it.
Do we have to put all square for everyone, or will there be a case when
I don't know if I know what you mean. Like, do you have to write it this way?
yeah,
If you wrote it like this, then you would get full marks. But this is a connection that you have to make for something else that you can't do the other way. But when we get there, we'll take a look at that. So for now, you can do this. If I wanted to do it like this, 1 and 4, 2 and 2, 4 and 1, 1 and 25, 5 and 5, and start looking, you could do that. But once you get this, it's way faster. Okay, last one. 9x to the 4th. Perfect square. Right? X to the 4th is perfect square. 9 is perfect square. 16. Perfect square. How do I check the middle term? Does anybody think they can do it? What do you think?
Square root of 16, which is 4, times square root of 9x to the power 4, which is 3x squared, and then times 2. That could be 24x squared. Put a negative on
Very good. Awesome. Okay, any questions about that? Special products, your special cases, important to know it. Okay, we're going to look at 2 more quick questions. I don't even need you to write them down. I just want to show you there's a couple to practice. These are harder ones. We're going to revisit them tomorrow, but I want you to have them in your head and start thinking about them now because they are trickier. B isn't really tricky. We've already kind of done one like that. But what about this one with fractions? You only ever really see fractions in this case. What do you notice about these fractions? Nice. There's two of them, minus sign between, and everything's a perfect square. That means this is still a difference of squares. What's the square root of 1 over 9? It's 1 over 3. You just take the square root of the top, square root of the bottom. What's the square root of 4 over 25? 2 over 5. Okay? You just take the square root of the top, square root of the bottom. Like, there's no fraction math here. You're just noticing perfect squares. So how would I write this? It's x over 3 plus 2 over 5. X over 3 minus 2 over 5. How do I multiply fractions? I multiply the top, I multiply the bottom, right? So taking the square root of them is easy. And the last one, what does it look like? It looks like a simple trinomial, except instead of x squared, it's x to the 8. But I'm going to give you this hint. It's the same idea. So can anybody think of two numbers that multiply to 40 and add to 3? Two numbers that multiply to 40 and add to 3. There's negatives here, right? So this is not the kind that I showed you earlier. That's not possible. Come on, people, think. We're almost done. Riley? 5 and 8. So here's what I would do. 8, 5, 5 and 8. What am I going to put in this first position? X to the 4th. Why? And it's going to be minus 8 plus 5. Because x to the 4th times x to the 4th is x to the 8th. And 5x to the 4th minus 8x to the 4th is negative 3x to the 4th. Okay, so the last thing that we're noticing, there's a couple like this in the practice today. The last thing that we're noticing is whenever that first exponent is double the middle one, it's the same pattern. X squared and x. X to the 4th and x squared. X to the 6th and x cubed. X to the 10 and x to the 5th. It'll always be the same. Does that make sense? Okay.